So the purpose of this lecture is to introduce the OLS estimator. You should have a good understanding of the linear regression model, and you should know about this idea of fitting an OLS trend line to data. So the setup is like this. We have a random sample, x1, y1 to xn, yn, n observations. X is the explanatory variable, Y is the dependent variable. We make the linear regression assumption, Yi is beta 1 plus beta 2 xi plus epsilon I, where beta 1, beta 2 are constants, unknown parameter, and the error term is denoted by epsilon I. We make the exogeneity assumption. That is, we do assume that the expected value of the error term is 0. So we're going to look at this linear regression model in terms of a simulation study. So remember that we view these xi as random variables. That's the way we think about a sample. And since it's a random sample, those xi's are independent random variables. They're independent of the other x variables. So to perform a simulation study, we are simply going to make an assumption about the distribution of these xi's. So in this example, we'll simply assume that all these xi's follow a normal distribution with, let's say, expected value mu, and the variance will denote that by sigma square and a subscript x, so we know it refers to the variance of the x's. They are IID, so that means that all the x random variables have the same distribution, that is, they have this normal distribution. So let's do a simulation where we simulate our x data from this distribution. To perform the simulation, I need a specific value for mu. So I'm going to have a value for mu here, and I need a specific value for sigma x. So I'm going to have sigma x here, not sigma x squared. So here I'll have the standard deviation for the x data. It doesn't really matter which numbers I pick. I'll just pick something. So let's pick for mu, I don't know, 10. And for sigma x, let's pick 2, so that the variance of the x variable is 4. My x variable will now on average be 10. That's the expected value, and I'll have a variance of 4. So now I can go ahead and simulate my x data. There is a way that you can simulate a random variable from a given normal distribution, and the formula is this. You type equal to, then you use the function called norm.inv. That's the inverse normal. You put a parenthesis. For the probability, you just type rand. That will give you random numbers. You put the mean that you want to simulate from, and that's this guy, B2. We can change that the way we want to. I'm going to copy this downwards, so I need a $sign on the 2. And then you put the standard deviation here, and that's B$3. That's the standard deviation. So once I hit enter here, it's going to give me a random number from this distribution, from the normal distribution with expected value 10 and variance 4. So it will be probably somewhere between 10 and 2 standard deviations. So I would guess I get a number somewhere between 6 and 14. We'll see. 7.33. This is going to be my x data. So this is my first x1. And yes, it will update every time I do anything, but that's okay. It doesn't really matter what these numbers are. And by the way, if you want to stop this automatic updating, you can just go to formulas and calculation option and set that to manual. But I'm not going to do that, so let's simulate data from the x variable. So I'm going to go down to 21. So I'm going to have n equal to 20. So here are n random numbers from the normal distribution. Since I've made these into parameters, I can easily change these parameters, and that will then change the x data. If I make this into -30, for example, then the x random variables will have an expected value of -30, and they will be around -30 instead. I don't want that. Take it back to 10. So this is the first part of my simulation study. I have now simulated my x variable. I cannot simulate my y variable in the same way because then I'm violating the linear regression model assumption. I have to simulate the y variable from this formula. I have this one. I also need this guy. So I need error terms. So if I simulate my error terms from a normal distribution and I pick the expected value to be 0, then because when Excel does random number simulation, it does it in a way such that these individual drawings are independent of each other. So if I simulate my epsilon from a normal with expected value 0, then the epsilon i's will be independent of the xi's and the exogeneity assumption will apply. The variance of the error term, that's up to me. I'm just going to denote that by sigma square without a subscript. That's the most common variance term in econometrics, so that's why we reserve sigma square for the variance of epsilon. So let's do that. We can do that in very similar manner. We'll need a new sigma here. That's going to be the standard deviation of the error term, and let's set that to something so that the error term doesn't have as much variance as the x one. Let's set that to 1. So here's my epsilon, and I can simulate that in the same way. Norm dot s dot dist, not s, sorry, that's standard normal. Norm dot inv, and then you do the rand. For the error term, it's very important that this is 0, otherwise I violate the exogeneity assumption, and the standard deviation, that's $4. So that's my first error term. I can just generate the other ones. So for example, this first observation is hit by a negative error term, second one with a positive, 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 so on. On average, there will be 0. Moving on, to get the yi random variables, to simulate that, I need to specify some numbers for beta 1 and beta 2 to carry out the simulation. So let's do that. I'll just specify some numbers here. Doesn't matter what I do, just do some numbers. Let's do an intercept of -4 maybe, and maybe a slope of 2 perhaps. And that allows me to specify or simulate the final random variable. So I need to simulate that according to the linear regression model, which is beta 1, that's B5, $5 plus beta 2, $6 multiplied by the corresponding x value I forgot to put an equal sign here. Multiply by the corresponding x value, add to that the error term. That will simulate y data, which is consistent with the linear regression model and an exogenous explanatory variable. So copy that down. So we can make a scatter plot of the x and y data. Just do an insert and a scatter plot like that. And here is the scatter plot. So this is the way you can think about the linear regression model. You can think about it sort of as a game that you play with nature. So nature tells you, this is sort of the starting point of the game, I am going to think of two numbers that I'm going to call beta 1 and beta 2, and I want you to guess which numbers I'm thinking of. So to you as an econometrician, those two numbers are unknown, so let's just paint them not yellow, but let's paint them red. They are unknown to you as an econometrician. So the next part of the game is then this. Nature says that, okay, so what I'm going to do now is I'm going to simulate some X data, and I am going to simulate some Y data. I'm going to simulate some Y data from the linear regression model. So I'm going to use these true values of beta 1 and beta 2. In my simulation, I will also use these parameters, which I'm not going to tell you. So these will be red as well. I will simulate errors, which I'm not going to tell you. So these will be red as well. But I will tell you the values of x and y. So I give you these guys. I give you x data, I give you y data. So let's paint that green. A bit dark. Okay, that's fine. So this is what you get from nature, this and this. And your part in this game is try to guess these two values. Well, if you're given this green data, it kind of makes sense to plot that into a scatter plot like this. So now think about this. How would you, based on this scatter plot, estimate or guess the value of beta 1 and beta 2 that nature has used to simulate this data? This really replicates the actual empirical situation that we are facing. Because I actually, when I do empirical work, observe data from an x variable and data from a y variable. And if I make the linear regression assumption, I actually assume that this data has been generated exactly the way we have illustrated in this Excel sheet. And the task that I'm facing as an econometrician is trying to reveal these two numbers. So this game, the way we think about it as a game, is representing the actual empirical work that we do as econometricians. So one way to play this game, one way of guessing the beta 1 and beta 2 is to realize that I have a bunch of x data. I have a bunch of observations on the x-axis. The deterministic part of the linear regression model, this part here, the conditional expectation of y, well, that's just a linear function. So there is a linear function here in the background whose intercept is beta 1 and whose slope is beta 2. And if you take a particular x value here, we'll go up to that one, and this will be the conditional expectation of yi. That's going to be the beta 1 plus beta 2 xi. That is, however, not the value we will observe, because we also have an error term for each observation. We know that this error term on average is 0. So for some observation, the error term is positive, taking us to this value, which is then the value that we actually observe for yi. But for another one, say for this particular value, xj, the error term could be negative, taking us to this value of y. So we end up observing these points. They're all sort of along the line. Some are above, some are below, simply because we have this error term. So we've seen this problem before. We've seen a case where we observe a bunch of points in a scatter plot, and we played around with this trying to find a trend line that fit this data. So a reasonable thing to do would be simply to fit a trend line to the observed scatter plot. Not cheating here, because I'm just using green data. So I'm adding a trend line, I'm displaying the equation on the chart, and that's what I need to do. So let's just do this. So this is the trend line. It has a slope of 1.75 and an intercept of minus 1.4. So that would be my guess. My guess for beta 1 would be this number here that we call B1, the OLS estimator of the slope. 1.75, that's my guess for beta 1. Sorry, I'm saying that incorrectly. That's the slope, so that's B2. The B2, that's my estimate for beta 2. The true value is 2, my estimate is 1.75. This part here, that's the one we call B1. That's the estimate of beta 1, so that's the estimate of this unknown minus 4. So one of the key points here is that in the, let's write it here, LRM plus exogeneity, if I have a linear regression model and exogeneity, I can estimate beta 1 and beta 2 using the OLS formulas B1 and B2. Remember, these B1 and B2 were just calculated from the data according to this formula, xi minus x bar, yi minus y bar, over summation xi minus x bar squared, and B1 was calculated from this formula. Those are my estimators. B2 is my estimator of beta 2. B1 is my estimator of beta 1. So don't confuse beta 2 with B2. They're really different things. Beta 2 is an unknown constant that only nature knows. It's just a number. B2 is something that we calculate from the random sample, and we use that as an estimate of beta 2. So one of the nice things with Excel is that you can redo the entire simulation study by just clicking on the F9 button. So if I click on the F9, the whole thing will just be redone. It will simulate new random variables from X, new random errors epsilon, it will calculate new Y values, and it will then redraw the scatter plot. So unfortunately, it doesn't update the equation of the trend line, I think. Let's Let's do F9. You get new numbers, but it doesn't update. So let's remove this and let's write it in terms of a formula which does update it. So I can put that here, B2, B1. And just by doing the linest function, linest the known y's. You see I'm only using green data here. Known x's, we want a constant and no statistics. Shift Control Enter. So by just clicking the F9 button, we can redo the entire experiment. And let's focus on the B2 because that's an estimator of beta 2. So in this case, we over guessed it a little bit. We guessed 2.2 when the true value was 2. If we redo the experiment, we over guessed it again, 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 again. Come on. I'm beginning to suspect that there is a problem here because we shouldn't overestimate it every time. Again, okay, so now we underestimated it. Again, well, on average, we should overestimate it half the times and underestimate it half the times. A property of the OLS estimator that we will call unbiasedness, and we'll look at that in a later lecture. One thing that we can note already now is the influence of this sigma, the standard deviation of the error term. If I take this down, let's say from 0 to 0.1, so I'm making the variance of the error terms much smaller. That means that they will now be much closer to 0 on average. Check the epsilon in the E column and check what happens when I take this down to 0.1. You see that they all become much smaller on average. Well, what happens in that case, if you get smaller errors on average, if you look at this picture here, if these errors are small on average, just go like up and down a little bit, well, that means that my estimated trend line must be closer to the true one. And that's one thing you can see in this case. You can see that now B2 is much closer to beta 2. The same is true for the intercept as well. If I do redo simulations in this case, you can see that every time my estimator gets really close to 2. It's very easy now to estimate beta 2 when the variance of the error term is so small. The opposite is of course also true. If I change this to something really big, then the error terms becomes really large, have large epsilons, and the B2 becomes much worse. It doesn't do as good a job anymore estimating the true value. We have a much bigger spread now in the XY scatter plot. We can do a little bit more than this actually, because when we did the trend line, we also discussed the concept of fitted values and residuals. So let's try to figure out what they correspond to in the linear regression model. So I'm moving this to the side a little bit here. First, let's take this down a little bit so we can see what's going on. I'm going to add a new column, which is the expected value of y given x, the conditional expectation. Remember, the conditional expectation is beta 1, so that's $5 plus beta 2, $6 times the x value. That's the conditional expectation of y given x. If we have exogeneity, which we do have in this case, so that's this value. Copy this down. So think about this for a second. Which color should this be? Do I know the conditional expectation? The answer is I do not, because I have used red numbers, so I don't know this one. So we need to paint that red. These are unknown. Let's do fitted values. Y hat. The fitted values have precisely the same formula as the conditional expectation, with one difference. They do not use the beta parameters, they use the estimated B's. So I need to change that to B1, which is in B11, plus B2, which is in A11, $11 times the X value. Copy this down. So this is green, because now I'm just using green numbers. Can even paint these greens because those are calculated from green data. So let's paint this green, and let's paint this green. Like that. Now if you look at this, you see that the fitted values are typically close to the conditional expectations. And that's not surprising. That's simply because the OLS estimates are in general pretty close to the betas. The B's are close to the betas, which means that the Y hats are close to the conditional expectations. And that is what they are. The fitted values are simply estimates of these conditional expectations. So this particular number, well, the way you should think about that is simply as an estimate of the conditional expectation of the Y value given that particular X value. That is what we would expect to see Y for this given X. We actually did see a lower value of Y than what we would expect to do, simply because that guy was hit by a negative error term. We also talked about the residuals, and those were denoted by E. It's really important to keep these apart, the error terms and the residuals. Very different things. The residuals are the Y value minus the fitted Y value, like that. It uses only green data, so we can paint that green as well. And if you look at the residuals, they tend to be pretty close to the error terms. Again, that is not surprising. The residual is the difference between Y and Y hat, while the error terms is the difference between Y and conditional expectation. Since these two are pretty much the same, epsilon and E will be very close. Some people even say that the residuals are estimates of the error term. I probably wouldn't go as far as that, because estimating the value of a random variable doesn't really make too much sense. We estimate unknown parameters. So let's just say that the error terms in general are close to the error terms. The sigma, the standard deviation of the error term, plays the same role here. If I take this down, say to 0.1, then the fitted values will become even closer to the conditional expectations, and the residuals will be much closer to the error terms. You can see that in this little example. So let's try to summarize what we have learned from this simulation study. The first key idea from this lecture is that you can view the linear regression model as something called a data generating process. What we mean by a data generating process is simply that it's a specification or a recipe, if you like, for how to simulate data from a random variable. In this case, it tells us precisely how to simulate data from the y random variable. The linear regression model doesn't really care at all about how the x data is simulated. The x variable is exogenous, so you can simulate that any way you like. Nothing will change in this experiment if you simulate the x data from a different distribution, say from a uniform, or if you just make up some x data, however you simulate or get the x data. The same goes for the error term. You can simulate the error terms any way you like, as long as you're careful in terms of making the explanatory variable exogenous. That is, this will happen if you make the x variable and the error terms independent, for example, then it will happen. And if you also make the expected value of the error term 0, then that will be the case. The important part is how you simulate the y data. And that's why we think about the linear regression model as a data generating process. You have to simulate data according to this formula, and that's the data generating process for y. The second key concept is this idea of estimators for the unknown parameters. So the second key idea is that this B1 and B2, the OLS values B1 and B2, those are estimators of beta 1 and beta 2. We use them, we use the values to guess beta 1 and beta 2, which are unknown to us. So in the linear regression model, the OLS estimators B2 is an estimator of beta 2, and the OL estimator B1 is an estimator of beta 1. Really important point here is that those are only two possible estimators. Or put it differently, B2 is only one possible estimator of beta 2. It's not the only one. We will meet other estimators of beta 2 in the course, and an important part of econometrics is knowing when to pick which estimator. So all we're saying right now is that B2 is an estimator. We haven't said anything about it being the best estimator, or we haven't said anything about under which circumstances we would use this estimator. So keep this in mind. We have many other estimators for beta 1 and beta 2 in the linear regression model. Although it's definitely true that the OLS estimators are the most common one. So not only can we view B1 and B2 as estimators of beta 1 and beta 2, we can also view the fitted values, B1 plus B2 xi, as estimates of the conditional expectations, which are beta 1 plus beta 2 xi. Well, kind of obvious because B1 is an estimator of beta 1 and B2 is an estimator of beta 2. Looking at this relationship for an arbitrary value of x and y, an arbitrary, not necessarily a sample point, we can also say that y hat without the index I calculated as b1 plus b2x. So this is just the fitted value of an arbitrary x value. X doesn't even have to be in the sample. That is going to be an estimate of this one, beta 1 plus beta 2x. And this part here, b1 plus b2x, well, that's exactly what we called the linear trend line. And what we can see is that that is an estimate of the true relationship between the x and the y variable. We will not reveal the exact relationship between x and y. We're not going to reveal beta 1 and beta 2 exactly. We'll only get some approximation. So b1 plus b2 will be close to beta 1 plus beta 2x, but not the same. So this holds then for arbitrary values of x. Finally, we also have a relationship between the fitted values, between the residuals and the error terms. So the residuals are these guys, yi minus fitted yi, or yi minus b1 minus b to xi, at least after fixing that sign. And we have error terms given by epsilon I is yi minus beta 1 minus beta 2 xi. Well, if b1 is close to beta 1 and b2 is close to beta 2, ei is close to epsilon I. So keep this in mind. It's a really important distinction here between the residuals and the error term. The residuals, we can actually calculate those. Those are based on our estimated trend line. The error terms are the things that affect y that we do not control for. Those are unknown to us. Finally, one of the most important ideas from this lecture is the fact that we really need to view b1 and b2 as random variables. We have to view them as random variables. Why? Well, it kind of follows from this simulation study. Beta 1 and beta 2, those are not random variables. Those are fixed, constant, even though they are unknown. But the x data and the y data, the random sample, those are random variables. If I redo the experiment, I will get new numbers for the x and the y. And that also means that I will get new numbers for b1 and b2. There is no way that you can know what value you will get for b1 and b2 until you have actually performed the experiment. And if you redo the experiment, you will get new numbers for b1 and b2. So b1 and b2 are known only after the experiment has been performed, and that's why you need to view them as random variables. Basically, anything that changes when you hit the F9 button, anything that changes here are random variables. So we have random variables everywhere except for these numbers in the B2 through B6. Those are just non-random constants. So even though not as important, it's also true that fitted values and residuals are random variables.